math, it's all about math, 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 wonderful world of math. Welcome to the wonderful world of math. It's probability day at the math studios. We're going to do conditional probability and contingency tables specifically. So what is conditional probability? Remember from before when we talked about conditional probability, if there is such a time, this notation, P of F given E, denotes the probability that event F happens, assuming that event E has already occurred. So this is not just the probability of F, it's assuming that E has happened in the universe where event E has occurred. What is the probability of F? In general, we have a multiplication rule for any two events, E and F. The probability that E and F both occur is equal to the probability that E happens times the probability of F given E. There is a multiplication rule for independent events, but this multiplication rule does not depend on the independence or dependence of the two events. It works for any two events. These are the two rules we're going to practice here with our contingency tables. So our example we're going to start with is a Bananatown College Cafe is rebranding a day of the week to compete with Taco Tuesday. The contingency table below shows the number of students who voted for each of the new choices, separated by academic division. So we've got mac and cheese Monday, mashed potato Monday, fish and chips Friday, and wonton Wednesday. So these four options are going to be the columns. The rows are divided by the academic division, like we said, humanities, arts, social sciences versus science, technology, engineering, and math. So everybody in this row was in one of these majors, and everybody in this row was one of these majors. All of these people voted for Mac and Cheese Monday. So these 323 people voted for Mac and Cheese Monday, and these 232 people also voted for Mac and Cheese Monday, but they were in different majors. Okay? Does that make sense? Great. So now we begin the questions. Number 1. What is the probability that a randomly selected student is a Haas major? In order to answer this, we have to figure out how many of all of these students were Haas majors. We need totals. We need to figure out how many do we have when we add up all of these different preferences among all of our Haas students surveyed. Once we find out how many Haas students we have altogether, we can figure out how many students we have total. So STEM majors plus Haas majors is going to be the total number of students in the survey. We'll need the number of Haas students and the number of total students to answer this question. The probability that a randomly selected student is a Haas major is going to be the number of humanities, arts, and social sciences majors divided by the total number of students. That would be the number of students in the sample space here. So let's find those totals. How many Haas majors do we have altogether? When you add up these people and these people and these people and these people, those are all the votes from all the Haas majors. And when you add them up, you should get 1,000. You'll want to add up all the people in this row. You'll want to add up all the people in these columns for later. How many STEM majors do we have altogether who voted? If you add up all of the people in this row, you should get, wait for it. Did you get it? Yeah, okay, good. 747 if we did it right. So then the total of the Haas majors and the STEM majors from these subtotals is going to be 1,747 students total altogether. When I add up each of the column subtotals, starting with 555 votes for Mac and Cheese Monday, the total of the column subtotals should also be 1747, so you can check your work like that. So go ahead and find these other three and check that this plus this plus this plus this is equal to the total number of students also. And in 3, 2, 1, let's check. And when we add up each of these four numbers, we should get 1747. Now, with these totals, we can figure out this probability. How many Haas majors altogether? Well, that was this number, the row total, 1,000. And how many students in the sample altogether? How many total? That was a total. So, 1,000 out of 1,747, this is the probability that a randomly selected student is a Haas major. Approximately 57.24%, or 0.5724 as a decimal. So let's see now if we can take that same principle and apply it to question 2. What is the probability that a randomly selected student preferred Wonton Wednesday? So you got to look at the probability of Wonton Wednesday as the number of people who preferred Wonton Wednesday out of the total number of people, right? This was the definition of probability for classical probability, or theoretical probability. So what's the total number of people who preferred Wonton Wednesday out of the total number of people? And rounded to 4 decimal places, we get approximately 47.97%, or 0.4797 as a decimal. Yeah? Great, grand. Good. Ready? So, the third question. What is the probability that a randomly selected student is a Haas major and voted for Wonton Wednesday? Which of these numbers in our table does that correspond with? Voted for Wonton Wednesday and was a Haas major. So, all of these people were voting for Wonton Wednesday. These people were voting for Wonton Wednesday, and they had a certain major. These people voted for Wonton Wednesday and had a different certain major. The people who voted for Wonton Wednesday and were a Haas major are represented by this cell here, the Wonton Wednesday column and the Haas Humanities, Arts, Social Sciences row. This cell corresponds to that and. Right? The Wonton Wednesday column and the Haas row, and we see the 482 people who are in that intersection of that column and the row. So the number of people in that cell was 482 out of the same total number of people still. And not that this is really the important part, but that fraction is approximately 27.59%. Now the first 3 questions were just kind of like warm-ups. Can we read contingency tables? Because the next question is going to involve the new stuff, the conditional probability. What is the probability that a randomly selected student preferred Wonton Wednesday given that they were in a Haas major, that they were Humanities, Arts, or Social Sciences? Now if you'll recall the notation we used for conditional probability, this second one was the assumption. The probability of F, assuming that, or given that, E has already occurred. So it says here, trying to give you a nice easy phrasing for the first one, the probability that a student preferred Wonton Wednesday, given that they were in a Haas major. Given that, this is our second event E. This is our assumption. So we're looking for the probability that somebody preferred Wonton Wednesday, given that they were in a Haas major. This is what we're looking for. So what this assumption does for us, it says that this is now our universe. We're now ignoring everybody in this survey that wasn't in the Humanities, Arts, or Social Sciences majors. Our universe has now become this row. These are the only people we're talking about now out of this group. What is the probability that a student in this group preferred Wonton Wednesday? So these are the people who preferred Wonton Wednesday that were in this group out of how many people altogether were in this group. So once again, if this is my entire universe, the people who preferred Wonton Wednesday are only these people. How did we describe this cell before? You remember? We said that this was Wonton Wednesday and Haas. That intersection. So the people in this universe that prefer Wonton Wednesday are the people who had Haas major and Wonton Wednesday preference. If this is my entire universe, the sample space has changed also. The sample space now is restricted to these 1,000 Haas majors. So when we go to use the classical probability rule, the number of things that satisfy this have to also be in this universe, right? So that was going to end up being an and. And the sample space, as we said, has been altered. Now it's the 1,000 Haas majors. That is what this conditional probability looks like from a contingency table. This condition narrows my view to a single row or a single column, in this case, the Haas row. In general, you're going to get the number of things in the intersection of the two events, the common outcomes, and divided by the number of things in the adjusted sample space, the new universe, E. And we'll come back to this in general thing in a minute. So how many people preferred Wonton Wednesday and were in the Haas division? Well, that was 482. How many people were Haas majors altogether? That was 1,000, right? So we've got 482 out of 1,000. That should be pretty easy to divide. So this is the probability of Wonton Wednesday preference given that the student was a Haas major. Now, back to the in general for a second. Suppose that I've got a fraction, a over b, and I wanted to say, do something weird, like divide the top and the bottom by the same number, or multiply the top and the bottom by the same thing. Let's suppose I wanted to multiply the top by 1 over c, and I wanted to multiply the bottom by the same thing. Because 1 over c over 1 over c is equal to 1 for any non-zero number c, we get a being a over 1, and b being the same as b over 1. This is just a over c over b over c. It's that a over b is the same as a over c over b over c. Alternatively, if I start with x over z over y over z, two fractions in the top and the bottom that have the same denominator, we experience dividing with fractions as multiplying by the reciprocal of the denominator, right? The reciprocal of the divisor. So what we would do to simplify that compound fraction like this is that instead of dividing, we would multiply, right? At which point you see that the z's are common factors from top to bottom, and this just becomes x over y. So here's both directions of this being equal. The point of this is that if I multiply the top and the bottom by 1 over c, the correct c, a helpful number, or rather, if I divide the top and the bottom by the same helpful thing, I can get a different version of this that is helpful in different scenarios. If I divide them both by the number of things in the original sample space, the definition of classical or theoretical probability tells me that this numerator, that's the probability of f and e. And that denominator here, this is the probability that e occurs. So you can say that the probability of f given e is based on these cardinalities, these numbers of things, or you can say that it's based on these probabilities. Sometimes, like with contingency tables, this is the version you want to use. But if you're not using contingency tables, you might not have those actual numbers. Maybe you only have percentages, in which case this is really helpful. So now what I want you to do is take this and show that this version is equivalent to this for the previous problem. Probability of f and e and the probability of e were, not coincidentally, the answers to questions previously. This probability was the answer to number 3, and this probability was the answer to number 1. So you look them up, you fill them in, and you divide. You should get the same thing we got here. And then we divide these two things, and we should get exactly what we wanted, 0.482. Alright? So these are two alternate ways to compute it. If you have a contingency table, this is usually easiest. Do that. But I also wanted you to see that they are equal. We've got 3 questions left before we close this out, and they should all be kind of a lot like the last one. What is the probability that a randomly selected student voted for Mashed Potato Monday, given that they majored in French literature? What kind of major is French literature? Is that a humanities, arts, social science, or is that a science, technology, engineering, math? Yeah, that's what I thought too. So, just like the last one, the assumption, given that, is that they were a Haas major. The probability that they voted for Mashed Potato Monday, given that they were a Haas major. So let's go look at our universe. The universe of humanities, arts, and social science majors has 1,000 people in it. Boom, boom, boom. There's the total number of people in the universe. Assuming that this is our universe, how many people voted for Mashed Potato Monday? These are the only people in the universe now that voted for Mashed Potato Monday. So the number of people in this row and this column divided by the total number of people in the universe, i.e. the row here, is 156 people in this row and this column, divided by the 1,000 people in this row. 156 out of 1,000, or 15.6%. What is the probability that a randomly selected student supports mac and cheese Mondays, like myself, given that they majored in engineering? Engineering is definitely a STEM, it's one of the letters, right? So this is our assumption, our given that. We're looking for the probability of mac and cheese Mondays, given that we had a STEM major. So we want the number of people who are both mac and STEM divided by the total number of people in the universe. The universe has been restricted to STEM majors, so we're going to look for the number of people in this row and this column, the single cell in the intersection. The STEM row and the mac and cheese Monday column, and there's 232 people that were in both, the intersection, divided by the 747 people who were STEM majors in this survey, which, rounded to 4 decimal places, is approximately 31.06%. So here's our last one. I would like you to try to decipher this, find the assumption, and the F and the E in the probability of F given E, label it, and then go look at our contingency table, find the row and the column that you need, look at the totals. Which totals do you need? Try to do this one by yourself, and we'll check together in just a second. So, what is the probability that a randomly selected student was a STEM major, given that they were a fan of Fish and Chips Friday? Okay, let's see if we got the notation right. You ready? 3, 2, 1, flip. Last time, the STEM major was the assumption. This time it is not the assumption, it's the other way around. Fish and Chips Friday is the assumption. So this time, STEM major is not going to be the universe. The universe is the column Fish and Chips Friday, meaning that the sample space now consists of everyone altogether who voted for Fish and Chips Friday, and that the cell in question is the one at the intersection of the row and column, that is STEM and Fish and Chips Friday. So if you didn't get that right, here's your second chance. Go ahead and make sure you can find these numbers on the table. Rewind if you have to. Ready? 3, 2, 1, flip. 129 people were STEM majors who also voted for Fish and Chips Friday, out of 168 people who voted for Fish and Chips Friday altogether. This is approximately 76.79%. So we've got 2 more things we want to do before we sign off today. And the first is try to rephrase this question. This isn't the only way I can ask it. I can also take this question and ask it, what is the probability that a randomly selected student who voted for Fish and Chips Friday ... was also a STEM major? So here, we're establishing that we're only considering students who voted for Fish and Chips Friday. And then they could also do some second condition. So only considering students who vote for Fish and Chips Friday means that that is our assumption. Just like when we said, given that event E, we can say that we're only considering students who voted for this. Or, instead of saying, what is the probability that a randomly selected student, I'll start by saying, what is the likelihood or probability that a randomly selected proponent of Fish and Chips Friday was a STEM major. I've already automatically narrowed the pool to only the people who voted for this thing. So those are some other ways that I can say that. Your job, though, is to be on the lookout for different ways we might say that. Next question. Are voting preference and academic division independent? We've talked about dependent events versus independent events. And the actual variables themselves are hard to separate. And especially with a sample like this survey, it's hard to do that. We'll learn how to do that later on when we learn inferential statistics. But for right now, we can look at events, specific events for this survey. So here we have an event E. Let E be the set of all people such that, or students in the survey, such that X is a Haas major. And F is a set of all students in the survey X, where X is the name of a student who voted for Wonton Wednesday. So here's two events. Is a Haas major and F, Wonton Wednesday. Are these two events independent? We had a vague definition of independent before, but here we have a nice precise definition of independence for two events. Now that we have this conditional probability language, the probability of F, assuming that E occurs, is equal to the probability that F occurs regardless of E, yes or no, means that E and F are independent. So this is what we want to check. For this question here, we want to check that condition. So these are the two things that we're looking for. We actually found both of these probabilities earlier. We just need to write them down here and see if they're the same. Here's the probability of F given E, and here's the probability of just F. So you'll see that these two probabilities are close but not the same, which tells us that these events are not independent. So our conclusion looks like this. These are not the same. So F and E are not independent. They are dependent. That's how we check. We look at P of F and we look at P of F given E. Are they the same? If yes, independent. If not, not independent. Cool, PJ? Good. Great. Grand. That actually concludes our stuff for today. We talked about contingency tables, we talked about conditional probability, we talked about independent events. Our constellation of the day is Centaurus, the Centaur constellation. This has been a Badger Bear production of the Wonderful World of Math. So now we're going to make like Wanda and the Whiners and join you on the flip side. Bye for now.